All right, guys. So, I was reading the news today. I came across an interesting study that just came out. Some researcher, some PhD doing research into education at Drexel University was studying the brains of students that are learning math and physics. So this researcher, he did MRI studies, functional magnetic resonance imaging studies of these people's brains as they were learning math and physics, and found that it actually increases activity to parts of your brain that you normally wouldn't. So the reason I mention this is kind of another motivation for why we learn math and calculus. You might have noticed I try and give you examples to show where you might use this stuff in like an engineering problem, but there's actually a whole nother motivation for this class. You may never take another integral for the rest of your life after you finish this class or whatever 20 series class you have to do. But you will still have learned a very important skill here, namely complex problem solving. And there's a graph which I probably should have shown you guys at the very beginning of the class of the skills that employers find most valuable. And I looked at this list. There's a list from 2015 and also a projected skills list for the year 2020. And on both of them, the very first skill, the most desired, most important skill was complex problem solving. So you could say that what you're learning here in this class is really just like life skills. And as this new study that I was just reading about shows out, like doing math literally expands your brain. Or, okay, maybe it doesn't actually like literally make it bigger, but it expands your mind, right? It sends blood to parts of your brain that normally don't get activated and thus strengthen those pathways. The brain is kind of like a muscle. When you use it, it gets stronger. So you might have noticed if you guys are doing your homework and you're like really thinking hard about a problem and you're working hard, you'll get hungry from doing homework, because you burn calories from thinking hard. So that's you exercising your brain. So that's another benefit you guys should be getting out of this class. Okay, so that's my little push for learning math. Before I get into the more of this series business, I thought I'd mention I did post another little extra credit assignment to watch one of those videos on YouTube, because the timing couldn't have been more perfect. Like just after the lecture where I was showing you those series formulas, like 1 minus a third plus a fifth minus a seventh, that this was equal to pi over 4. And also in the same lecture I was talking about 1 plus a fourth plus a ninth and so forth, how this was pi squared over 6. Right after I was talking about this, I see this YouTube video, this 3 blue, 1 brown video, where he talks about both of these formulas and a few other formulas that involve pi. So just because the timing was just so perfect, I had to give it to you guys. So you'll see that on WebAssign, and as usual, you'll have like a week to do it. Watch the video, answer a question, get a couple more points. Okay. Any questions before we get into it? All right. So today we are on section 10.5. These are more limit tests, or was it convergence tests? As well as kind of like a wrap-up of all the different tests we've learned and when to apply them. So that'll be kind of a review, which I'll do at the end. Okay, so let's see. I usually kind of like, before giving you a new theorem, I'll usually try and motivate it. So let's start off. Let's start off by doing that. Here's an example of a series that we want to talk about. So let's look at, what was it? Okay, so here's the motivating example. How about this one? 2 to the n over n factorial. So this looks like 1 plus 2 over 1 plus 4 over, here, let me write it like this. 2 squared over 2 factorial, 2 to the third over 3 factorial, 2 to the fourth over 4 factorial, so forth. Okay. So how about let's just see if we can guess. How are you guys doing on your intuition? And the question, of course, here is, does it converge or not? It is clearly a sum of positive terms. So there's either two possibilities. It either converges or it blows up to infinity. Those are the only two possibilities. What do you guys think? Converge? Anyone think it converges? Okay, anyone think it does not converge? Oh, okay, all right. Well, you guys have pretty good intuition. I think I'm going to do a problem later today where I'm going to ask you guys to close your eyes and raise your hand as to what you think, because I kind of want to get a honest poll on how you guys are doing on your convergence tests. But we'll get to that later. So most people suspected that this one converges. Problem is we don't really have a way to show that yet. Right? We've got a couple of our tests that we've learned, like the comparison test and the limit comparison test, but those actually won't work for this one. We need a new one. So there's going to be 2 new tests today that we're going to learn, and then that's going to be all of them. So the new one is called the ratio test. So here's what the ratio test says. So we have a series where the terms are labeled AN, and as the name indicates, we're going to take the ratio of 2 consecutive terms, okay? So let's use the letter, anyone know what Greek letter this is? This is a rho. This is the Greek letter rho. It looks kind of like a P. So, okay, so we're going to let rho equal the limit of the ratio. So you take consecutive terms. So how about the n plus 1th term and the nth term? Okay, and then there are 3 possibilities. So if rho is less than 1, then the series converges. In fact, it does something even stronger. It converges absolutely. And if you remember that's an even stronger notion than converges. Okay. Second possibility is it's greater than 1, in which case the sequence diverges. Wait, let me double check something. And thirdly, it can equal 1. So it's either bigger than 1, less than 1, or equal to 1. And the equal 1 case is a borderline case where actually you don't learn anything from the test. The test is inconclusive. It doesn't tell you. So as we'll see, there are cases where the limit is equal to 1 and it diverges, and there's cases where the limit's 1 and it converges. So either one can happen in this third possibility. So all right, let's apply it to our example. Anyone still need this 20B SI? Yeah, I should go to it. So in our example, an was, what was it? 2 to the n over n factorial. So, okay, here's how it works. If this is an, then the n plus first term, so we'll just replace n with n plus 1. It'll be 2 to the n plus 1 for n plus 1 factorial. Okay, now let's take the limit, or sorry, the ratio, excuse me. The ratio of an to plus 1 to an. It's all positive, so we can disregard the absolute value. 2 to the n plus 1 over n plus 1 factorial over 2 to the n over n factorial. Okay, so this is, here, let's write it like this. 2 to the n plus 1 times n factorial over 2 to the n times n plus 1 factorial. So I get to cancel a bunch of stuff. I can cancel n of the 2's. And I can cancel all but the n plus 1 term from here. So I just get a 2 on the top and an n plus 1 on the bottom. Any questions on that cancellation? Yeah, Robert?
So the reason why you could remove the n plus 1 is because the n plus 1 factorial, like why?
So the n plus 1 factorial, this is n plus 1 times n minus 1, dot, 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 down to 2 times 1. So that's the same as n plus 1 times n factorial. Yeah, so I just was able to cancel off the n factorial with the 1 on the top.
And that will work for any factorial?
Yeah, yes, this is a very common this is a known property of factorials, which will be very useful when you apply this test. And in fact, this is kind of the prototypical example of when to apply the ratio test. As I'm going to talk about later today, whenever you see factorials in your sequence, that's a hint that's like, this might be the type of place to apply the ratio test. So this is easy enough to take the limit. As n goes to infinity, this goes to 0, which puts us in the first case, the convergence case, because 0 is less than 1. So 2 to the n over n factorial converges. Okay. Okay, let's going to do another example, but I think, let me get to the next test right now first, actually. So I said we only have 2 more tests. The ratio test was one of them. And the other one, the next one, the last one, is called the root test. It's kind of weird. You don't actually use it that often. But let me give you an example to show when you would want to use it. So the next example is the sequence, what was it? Oh, yeah, okay. So how about n over 3n plus 1 to the n. So this one, if we tried to do the ratio test on this one, it wouldn't work out very well. Like, we could try. Here, let's say I tried to do the ratio test. So in this case, the nth term is n over 3n plus 1 to the n. So the n plus 1 term is, okay, n plus 1, 3n plus 1 to the n plus 1. So the ratio of those guys, it will be, this whole mess. So n plus 1 over 3n plus 1 plus 1 to the n plus 1 over n over 3n plus 1 to the n. How you even do that? I mean, you could write that as n plus 1 over 3n plus 1 times n plus 1 over 3n plus 1 n over 3n plus 1 to the n. And you still have this big mess. Like this part goes to 1/3 as n goes to infinity. This, I don't even know. It's how to evaluate this limit as n goes to infinity, because it's got an n up there in the power. So you might like mess around with this a little bit more, but really you should just give up with applying the ratio test. Yeah, because we've got a, so I'm just going to give up. If only we had a test that was really good for when you had series that had like n's in the power, like some function of n to another function of n. So that's our last test. It's called the root test. Okay, so again, that's for a series, let's say with term an, and we let L be the limit. So this is kind of weird. It'll be the limit of the nth root of the nth term. And again, we have three possibilities. Actually, in fact, I think it's the same as these. The answer is actually the same as this, actually. Yeah. I should double check. Let me just make sure. I'll make absolutely sure I'm getting all my results right. Yeah. Okay. Yeah. So it's the same three conclusions actually. So if L is less than 1, then well, it's the same as if rho is less than 1. So the series converges absolutely. And in particular, it converges. If L is greater than 1, it diverges. And if L equals 1, the test is inconclusive. So yeah, as I said, it's the same three results for the ratio test. But let's So practice applying this one to my example. So there, an was n over 3n plus 1 to the n. So this is the quantity we need to calculate, right? You take the nth root of it. So the nth root of an, we don't need the absolute value because this is positive. So this is n to the 3n plus 1 to the n, but then the nth root of that. So the nth power and the nth root just cancel each other off. And this is n over 3n plus 1, which goes to, what does this go to? 1/3. So by the first condition, the series converges. Yeah, right. So that's a pretty common, you'll see like that those conditions kind of keep on reappearing over and over again. Okay, let's see, what am I doing next? Mm-hmm.
Will the n and to the nth term, the root n and to the nth term always match so that they can cancel? Or what if it's like to the 3n or something like that?
Okay. So what if it was to the 3n? So let's see what happens. What if this was a 3n? So this was a 3n. So what would it be? This is the same as n over 3n plus 1 to the 3n to the 1 over n power. So the n's would still cancel, but we'd have a to the third here, which would converge to 1/3 to the third, which is equal to 1 over 27. So in that case, we would still be able to apply it. Yeah, it's a good question. Yeah, you could imagine seeing different powers. Maybe it was n plus 1 or n squared. Oh, yeah, what if it was... Okay, you want to see what would happen if it was n squared? Let's see. How about if it was n squared? If it was n squared, so if it say n over 3n plus 1 to the n squared, and then we want the nth root of this, okay, so that's n over 3n plus 1 to the n squared to the 1 over n, and we would cancel one of the n's, and then it would be n over 3n plus 1 to the n. Yeah, and what does this go to? Kind of a good question. This, you guys know what this goes to as n goes to infinity? Sorry? Yeah, it was our original one, except now we're looking at the sequence. Right? Originally, we were looking at the series, the sum of those terms, and we found that sum converged. Well, the only way that this sum is going to converge, if this sum will only converge if the terms go to 0. Right? We already found out in the original example this converges. Therefore, the terms must go to 0. So that tells us right now this must go to 0. So I'm kind of cheating, right? Because I'm finding that this must go to 0 in a very indirect way, just because we already know that the series converged from the previous example. So So yeah, I kind of like this. All right. So since 3n plus 1 to the n converged, necessarily the terms have to go to 0. That definitely doesn't converge if the terms don't go to 0. So, okay, so we figured out that this goes to 0 as n goes to infinity. So what does the root test, the root test say for this? I didn't really write it. So for the sum, n over 3n plus 1 to the n squared, does it converge or not? Yeah, right, because the limit was less than 1. Okay, so I would say, so this sequence converges by the root test. All right, cool. Good questions. Glad you guys are asking those. Let's see here. Root test. Oh, okay. So now, okay, so that's all the tests. The rest of this section is just kind of a review of how to know which test to do. You know, like, remember back in chapter 7, we had all those different ways of figuring out integrals, and then I did a section which is like, well, how do you know which one to do? So let me kind of try and wrap up all these tests now with a discussion of how to know which test to do. So kind of be a review. Okay. So let's see. One thing that will definitely help you in figuring out which tests to do is to remember the ones where we already know the answer, right? So there's a few very common series. Namely a p series, 1 over n to the p, and then a geometric series, r to the n. These are both well known. So just like keep these examples in mind. Because, for example, if you want to use the comparison test, you might want to compare to one of these. So keep these examples in your back pocket, right? Let me just say. So this one converges when p is bigger than 1. This one converges. Who remembers, when does this one converge?
When r is less than 1.
Good, yeah. So yeah, when, and I'll allow it to be negative, so I'll say an absolute value. Let's see. Okay, so first thing, if let's say we're given some series, we don't know whether it converges, we don't even know what test to do on it, and you want to answer the question, does it converge? One thing you should probably check before you attempt anything else is just make sure the terms go to 0. Okay, so first rule, check that an goes to 0 as n goes to infinity. Because if it doesn't, then the series diverges. Okay. second thing is if it's a series of positive terms, which usually are, so if the AN are all positive, then we have a few different things we can try. Let's see, our first test for positive terms was the direct comparison test. So let me give you an example of when to use that, or an example of using that. How about 1 over n cubed plus the square root of n? How about, what should I compare this to? And let me get someone else. How about from farther in the back? Someone want to volunteer a good comparison for this one? Yes. Good, yes. So compare this with 1 over n cubed, right? Because this quantity right here is less than or equal to 1 over n cubed. Right? So this one converges by the p-test. Therefore, this one converges. All right. Okay, so after we learned the comparison test, the next test we had was the limit comparison test. By the way, I didn't write the comparison test, but let me just for completeness. So this is if AN is less than or equal to BN, then if the bigger sequence converges, the little one converges. The limit comparison test, which was, what was it? Oh, you, I want to write the whole thing. Right, you looked at the limit of AN over BN, and if, I don't want to write the whole thing again. Let me just do it. I don't want to write it again. I'll just say if 0 is less than L is less than infinity, then AN and BN do the same thing, have the same behavior. This is the usual case for this one. So that's when they both converge or both diverge. This isn't the whole limit comparison test, but I don't want to write the other two cases. We hardly even use them anyway. But let's do an example of this one. So how about let me modify this example a little bit. Basically, I'm just going to change this plus sign to a minus sign. So yeah, if I erased this plus sign and made it a minus, is this still true? I just messed up my comparison by changing it to a minus. Yeah, if I made this a minus, then I can't do this anymore. It's not true anymore. So for 1 over n cubed minus root n, we can't use the same comparison test, but as Sir up there pointed out, this is still a good thing to compare it to, because the n cubed is kind of the dominant power right here. So your intuition should still be having you reminded of 1 over n cubed, because when n is like a million to the trillionth to the zillionth power. If you cube that number, that's way bigger than the square root right here. All right, the square root is kind of insignificant once n is really big. So now, if we let bn just be 1 over n cubed, right, and this right here is an, so then an over bn, that's 1 over n cubed minus root n over 1 over n cubed. So that is n cubed over n cubed minus root n. Here, how about, let's divide everything by n cubed, how about? So I'll get 1 over 1 minus root n over n cubed. And this one, it's easily enough to take the limit. Right, this dies when n goes to infinity. So as we take n to infinity, this guy goes to 0, and the whole thing goes to 1, which is the case that we wanted, right? Which means that the two series are comparable. Okay. So 1 over n cubed over n, 1 over that guy. So that converges by limit comparison tests. Okay, what was the next test that we learned? The next one was the one we did today. So that was the ratio test. There's no need for me to write it again. We just did it half an hour ago. But you guys remember when I said is good for doing the ratio test? Factorials, yes. So this is good for factorials. So I got an example I kind of want you guys to do on this one. I think, yeah, this could be interesting. So this is like a classwork problem. I want you to do this. I'm going to give you a few minutes. So use the ratio test on the following series. Damn it. Okay, let's do n factorial over, this better be big on the bottom, whatever it is. So I just came up with this before class, and I didn't know beforehand actually what it did. How about n factorial over n to the n? It does actually go to the terms, right? N factorial over n to the n. If you looked at what these look like, it's like n times n minus 1, n minus 2, times 3 times 2 times 1. But the bottom is just n times n times n times n times n times n. So clearly, like the bottom is bigger, and you can see that it will in fact go to 0. But okay, what does the ratio test say? So there's 3 possibilities. Here's possibility 1, which is it converge. 3 possibilities. 1, it converges. 2, it diverges, and 3, the test is inconclusive. So go ahead and do this. Inconclusive. So you can talk to your neighbor if you want to. And I'm going to take a poll, see how many people can get this right. So give you a couple minutes.
Can you remind me what the rule was for the root test?
The root test is it's the same. If the limit is less than 1, it converges. If it's greater than 1, it diverges. If it equals 1, it's inconclusive.
Oh wow. Okay.
Okay, so I want to see how you guys did on this, but I don't want anyone to be embarrassed or ashamed. So I'm going to ask you to close your eyes and then have you raise your hand for one of these 3 possibilities. So how about everyone close their eyes, raise your hand if you thought it converges. Okay, put your hands down. Raise your hand if you thought it diverges. Put your hands down. Raise your hand if you thought the test is inconclusive. Okay, yeah, you can put your hands down. So FYI, about half the class said it converged, and about 25% said it diverged, and about 25% said it's inconclusive. So now let me do it. So the ratio test on this guy, if an is n factorial over n to the n, and an plus 1 is n plus 1 factorial over n plus 1 to the n plus 1. Okay, so then we take the ratio of an plus 1 over an. We don't need the absolute value because everything's positive. So this will be n plus 1 factorial over n plus 1 to the n plus 1, n factorial over n to the n. So this is going to be n plus 1 factorial over n factorial, and n to the n, let me write it like this, n plus 1 to the n. Is that right? I split off one of the powers of this term. So this is the same as, I can cancel out a bunch of the factorials. So I'll get an n plus 1 there. This term I'm going to write as n over n plus 1 to the n. This one is 1 over n plus 1. These guys cancel. N over n plus 1 to the n. Do we know what this limit is? This is the same as n plus 1 minus 1 over n plus 1 to the n, which is the same as 1 minus 1 over n plus 1 to the n. This, you guys recognize this? I think someone said it. Yeah?
The E?
It's something like E. Yeah, it's sorry?
Never mind.
I can never remember the freaking formula for it. E to the, let's say, x. This, now I haven't done this in this class, but maybe you've seen it. This is the limit as n goes to infinity of 1 plus, so like x over n to the n. Is that right? Does anyone remember? Oh, it is? Okay, so, wait, where did this just go on? So this is kind of like that one, but with x being negative 1. All right, so this is about, this tends to e to the negative 1, actually, as n goes to infinity. Technically, I should put like a n plus 1 right here, and then divide by this expression, which is a term that just goes to 1, so don't worry about that. So the point is, this is a number that is less than 1, so the ratio test says that this series converges. So all you guys that said it converged, you did good. Now don't pack up yet, I'm not done. So I want you guys to go check this this formula for E. And let's see, there's a couple other things we can do to evaluate whether a series converges. So to finish off this lecture, let's see, that was D. D, we have the root test, which I already did today. But let me just tell you what it's good for. It's good for when you have f of n to some other g of n. Those are the type of situations when you want to use the root test. And we did an example of that, which you guys participated in, and that was good. So I won't do that again right now. After that, we also had the integral test, which if I had more time, I would do an example with 1 over x ln x squared. But we're out of time, so maybe I'll save this for later, or maybe you guys could, because I like this as a test question. Maybe a good question to put on the final. And finally, let's see. If the terms aren't all positive, then there's the alternating series test. And you can also just test for absolute convergence. since that implies convergence. But I don't have time to do examples of those right now. So yeah, those are all your strategies for doing series.
Is telescoping series?
Yes, that's a good one. Yeah, that's a good technique, I guess. Yeah.
I don't know which category it falls into.
Right. Yeah.